and with her, I also started my research in cryptography. I didn't know much about cryptography before she came and became my PhD student. But after that, it turns out that this is a quite popular topic. And I had other students on master's level and on PhD level who were interested in it. And my most recent student is Sulaiman Alhussaini, who joined me last autumn. And much of what's going to be presented here is the result of my joint work with him, but it is based also on my joint work with Anya. So yeah, this is the plan of the talk. Hope I have enough time to present most of it to you. Time is always short. Yeah, in the introduction, I'm going to mention something about max plus algebra and the implementation of the Stickel protocol over max plus semiring, which is also called tropical semiring. Then the next topic will be attack on those protocols, because once protocol is established, an attacker or eavesdropper would like to use the information available to them through open channels to regenerate the keys generated by Alice and Bob. You will see more details about it. It will be more clear what I'm talking about. Yeah, another way of attacking Stickel protocol is to solve what we call the two-sided logarithm problem. And also I'll present cryptanalysis of a protocol which was published previously by different authors, but the techniques presented in the talk allow to break that protocol. And finally, we are going to extend Stickel protocols to semirings. The topic of the talk is semirings with idempotent addition. I'm going to start with max plus semiring, but at the end of the talk, I hope to come to more general semirings. Just different semirings, max min, max t, and symmetrised. Something will be said about it. Okay, so let's go to preliminaries. This is max plus or tropical semiring. We have two operations. New addition, which is defined as maximum of two numbers, and new multiplication, which is addition. Operations are defined over a real set with minus infinity element. Then this arithmetics is extended to matrices and vectors in the usual way, as it is done in linear algebra. In particular, we have tropical matrix powers. Tropical matrix powers, they will be important to us. The case tropical power is tropical product of matrix A with itself, taken K times. So yeah, usual linear algebra, but with unusual arithmetics. That's what it is essentially. To a matrix, we can associate a graph. This is what we quite usually do when we study matrix algebra. We associate a graph to a matrix. It has a set of nodes, which is set from 1 to n. And then we put an arc between two nodes whenever the corresponding matrix entry is not minus infinity. And then this matrix entry becomes the weight of the arc from I to j. The weight can be extended to paths on the D graph. So if you want to define the weight of a path, then you multiply matrix entries along the path, remembering that product in the tropical case is the same as addition, so means that we add the weights using usual arithmetics. Yeah? The length of the path is defined as the number of arcs in the path. If you have path from I1 so to I2 so on to IK, then the length is k minus 1. Right? And if the beginning and end of the path coincide, then the path is called a cycle. the maximum cycle mean of a matrix is defined as the maximum of the ratio between the weight of the cycle and the length of the cycle, and the maximum is taken of all cycles that are present in the associated diagram. Then, if the cycle happens to have this ratio exactly equal to the maximum cycle mean, that is, if the cycle has the biggest possible such ratio, weight divided by length, then such cycle is called critical, and the critical graph is a subgraph of associated graph, and it consists of all nodes and arcs which belong to critical cycles. Here's an example: a 3 by 3 matrix, and the associated graph is the complete graph on 3 nodes, and if you compute the maximum cycle mean, it turns out to be 2. The maximum cycle mean is obtained just at 2 cycles, so just 2 cycles are critical here, from 1 to 2 and back, from 2 to 3 and back. The maximum cycle mean is equal to 2. This is the weight to length ratio of any of these cycles. So yeah, I found it convenient to introduce these concepts right now in the beginning of the talk. Also because this will be used in one of the attacks that I'm going to present. And it also gives you some flavor of tropical matrix algebra and its connection to combinatorics of D graphs, so what kind of things we are considering when solving the problems of tropical linear algebra. Also, we can define Kleene star. It's defined as the formal series like that, formal series of where we have all matrix powers and we sum them up. And then it turns out that this series converges and can be truncated after power a to the n if and only if the maximum cycle mean is less than or equal to 0. So Kleene star is a tropical analog of I minus a minus 1. So it's a tropical analog of resolve. Right, so now to the cryptography. Alice and Bob, this is the Stickel protocol, but implemented using tropical matrix powers. So in the Stickel protocol on matrix powers, Alice and Bob choose. They agree on public matrices. Sorry, it looks like there is some technical problem. So Alice and Bob agree on some public matrices A, B, and M. These are square matrices, right? And then Alice chooses integers K and L and sends a message U equal to A to the power K multiplied by M multiplied by B to the power L to Bob. Yeah. And Bob does similar thing. Bob chooses his secret parameters R and S and sends a similar message, a different message, V, A to power R multiplied by M multiplied by B to power S to Alice. And then these messages are used again by both parties. So Alice uses the message which was sent to her by Bob to compute her version of the T. She does this using also her private secret parameters K and L. So the version of T computed by Alice is A to the power K multiplied by B multiplied by B to the power L. And Bob computes his version of the T using the message which he obtained from Alice and using his secret parameters R and S. Yeah, and magically these keys coincide. You might ask, why do they coincide? How did Alice and Bob end up with the same key, although they didn't exchange it over open channel? But they ended up with the same. That's the beauty of it. Yeah, and that's why this is used. Because there is no direct access to this key. Yeah. they just compute it, it turns out to be the same. Turns out to be the same because any two matrix powers of the same matrix commute. Yeah? So we have the commutativity property of matrix powers, which implies that the two versions of the keys, key computed by Alice and by Bob, are the same. And this is so over any semiring, because if you have a semiring, where in particular you have distributivity property, that A multiplied by B plus C is equal to A multiplied by B plus A multiplied by C. So you have this property. This property allows you to unambiguously define matrix power, and then any two matrix powers will commute, and you can implement this kind of protocol over any semiring using matrix powers over that semiring. No problem at all. There are also other ways how to implement the same protocol, the same kind of protocol. One way is using tropical matrix polynomial. This is the same as matrix polynomial, but with tropical operations of addition and multiplication. And yet another way is using circlets. So what's the circlet? If you forget about the parameter s, just for the moment, imagine that there's no parameter s appearing. Then what do you see? The first row is C0, Cn minus 1, Cn minus 2, so on, C1. And then the second row is this, and it is result of the cyclic permutation of the first row. So now we have C1, C0, Cn minus 1, so on, C2. Then you apply the same cyclic permutation again and again, and thus you generate all the rows of the circle. Right, and then with the S circlet, you multiply the upper triangle by extra parameter S. Turns out also that any two such matrices with the same parameter S commute. And this is true over any semiring. The proof is non-trivial and long, and you can find it in appendix of one of the works with Sulaiman, which we submitted to Cryptography archive. Right. So, yeah, since two polynomials of the same matrix commute, you can use polynomials instead of matrix powers. In Stickel protocol, this was one of the main ideas in the seminal paper by Grigoriev and Shpilrain, tropical cryptography. So if you want to learn about tropical cryptography, then you should start with this paper. Yeah, and in the circlet protocol using circlets, we just use modified circlets instead of powers or instead of polynomials. This version of protocol is very recent. It appeared in a work by Huawei Huang and his co-authors. Yeah, and what we did with Ani, we also considered other kinds of commuting matrices, in particular in the de la Puente matrix, which I will abbreviate as LDLP. So yeah, I don't want you to really delve deeply into the definition of these matrices. It's only important to us that these matrices commute. Yeah. Since these two matrices commute, we can also use them in Stickel. Whenever you have a class of commuting matrices in tropical matrix algebra, you can construct the Stickel protocol. The only problem with it, perhaps, is that if you want to use another semiring, then it may be difficult or not very obvious how to extend the same type of matrices to different semiring. Yeah. So you can read more about protocols using LDLP matrices and other types of commuting matrices in Ani's thesis, which is available online. Yeah, okay, so next, how to attack the versions of Stickel protocol that have been discussed. The problem of attack is that attacker cannot access the key produced by symbol. But the attacker can use of obviously the public matrices that Alice and Bob had to agree on before they implemented the protocol. And the attacker can also use the messages sent by Alice and Bob to each other. So those messages U and V. that they send to each other in the process of the protocol also can be used by the attacker. And the objective is to find the common key that they end up with and attack. Yeah. In the Stickel protocol in particular, attacker can aim to find good enough matrices X and Y that satisfy the relation X and Y is equal to Q. And if X and Y are good enough, then they will allow the attacker to compromise their exchange. Yeah. And what does it mean? Good. Yeah. Matrix used by Bob on the left, and Y should commute with the matrix used by Bob on the right. And you can write this how the commutativity is defined. So relations like AX equals to XA should hold, B or BY is equal to YB. But another idea is that since Alice and Bob are already using class of commutative matrices, why don't we just require X to be in the same class as the class of matrices that Alice and Bob are using? And we can also require that Y is from the same class that Alice and Bob are using on the right. And classes, commutative subsemigroup of matrices that Alice and Bob are using. It happens that such commutative subsemigroups can be generated by some elementary generators. There are some elementary matrices, such that any matrix in the class can be represented like this, by this kind of linear involving matrices. It just happens so. With Ani and with other co-authors, we haven't seen any examples when it's not right. So, therefore, the attack that uses this representation seems to be quite general. And sometimes we might meet some conditions on the parameters X alpha and Y beta. Anyway, when we plug these expressions for X and Y into the equation U equals to X and Y, then this is kind of equation that we get, right? So X alpha Y beta multiplied by this kind of matrix. This gamma alpha M gamma beta is known to us. It's known to the attacker. It's known to the attacker. What's not known is X alpha Y beta. X alpha Y beta are unknowns. Everything else is known, right? That's the problem of attacker, to find this X alpha Y beta. How to find it? Just denote X alpha multiplied by Y beta by Z. And then we will have something what we call tropically linear. Yeah. In the tropical case, you can also make the right-hand side equal to 0, as it is explained above. So then what's important is that we get a tropical linear matrix equation where the unknown Z alpha beta has certain structure. So it should be equal to X alpha Y beta. But otherwise, we have tropical system of the form AZ equals to B. And such tropical system is very easy. Like if you open any monograph on tropical matrix algebra, it's no-brainer for any author of the monograph to write out the greatest solution to AZ equals to B. But that's a popular topic. Many authors. What is less such system of equations is and to describe the whole solution set. And in our case, we are actually interested in the whole solution set because we need these unknowns to have special structure. So among all the solutions of tropical linear system, we need to find a solution which has this special structure, right? So then this is the basis of the attack. Yeah. In max class, minimal solutions correspond to minimal covers. And more precisely, what kind of minimal covers? What do they cover and how? let's answer this question. So at first in the attack, we compute these elements C alpha beta, which are a minima of the entries of matrices T alpha beta. So we have matrix T alpha beta, it has entries, and we need to compute a minimum of minus T alpha beta of all these entries. And then, like we always do in optimization, we see where the arguments of minima are, where the minima are obtained. This forms sets S. Yeah? And then in the attack, we want to find all minimal covers of the set of all entries n by n by these sets S alpha beta. Yeah? And then we want to find a minimal cover for which the following system is solvable. In the system, we have equation x alpha plus y beta whenever alpha beta is part of the cover C. And inequalities otherwise. On top of that, we also might have some conditions on x alpha and y. So this general form of Kotov-Ushakov attack was described in my paper with Anya. Right. So what's bad about it is that we want to enumerate all the minimal covers. And there can be a big number of these minimal covers. The problem of enumerating these minimal covers or finding the smallest possible minimal cover is related to heating sets or transversals of hypergraphs. So in the problem of finding smallest heating set of all minimal heating sets, we have a set of n elements denoted by capital V, and let curly H be a set, a collection of subsets, yeah, of V. In other words, this is a hypergraph, and then a subset capital X of V is called a heating set or a transversal if it has non-empty intersection with any set in the collection curly H. And then, so the problem of finding all minimal covers in the attack before is related to, it's more difficult than the problem of finding all minimal heating sets in this problem. The problem of finding all minimal heating sets is not that hard, but it can be solved in incremental quasi-polynomial time. The problem is that there are a lot of minimal heating sets. And the related NP-hard problem is finding the smallest heating set. Actually, finding the smallest heating set is also relevant to us because we would like to have as small number of equations as possible here. Actually, but yeah, what is more relevant is enumerating all minimal heating sets, so all minimal covers. To avoid enumerating all minimal covers, we might try to do something heuristic. Use an attack which doesn't necessarily work, but it does work in. We hope that it works for the protocol that we're trying to attack. Yeah. And then we can measure the success rate and so on. In this heuristic attack, we just find one cover. How to find one cover? So repeatedly you scan all pairs, all entries gamma delta. And then for each pair that is not yet covered, we find a set S alpha beta of the largest size which covers it. So thus we make an attempt, a bit naive attempt to find a cover of the smallest possible cardinality, the minimum cover, right? But it won't be minimum cover really, but yes, it turns out to be a good idea actually, just to find a cover this way. So the collection of all such S alpha beta forms cover. And then for this cover, we're trying to solve the system. Yeah. Solving this system is a linear programming problem. So it's not a problem to solve it. It's not a problem to find such a cover using this procedure. The only problem is that this is a heuristic. it won't really crack the protocol. It won't be guaranteed to do it. So when we do numerical experiments, then so performing Stickel protocol is okay. It's feasible for even for large dimensions like 100 by 100, but the full version of Kotov-Ushakov attack doesn't scale up. So for dimensions like 50 by 50, you will already wait for hours for the attack to break Stickel's protocol. And it's the same for protocol implemented using polynomials and for the protocol implemented using circles. The same story. Heuristic attack, however, is not the same story. So for polynomials, however, it turns to be quite successful already. Like 95% of success rate for heuristic version of attack on the protocol based on polynomials, and for circles it's overwhelming, 100%. Somehow it means that there should be a mathematical claim, there should be a theorem about it. There should be a rigorous explanation why the heuristic attack on circles always works. So linear-delocalente matrices, however, are a very different story. So Suleiman implemented Kotov-Ushakov attack on linear-delocalente matrices and heuristic version as well. Turned out that minimal covers, the number of minimal covers is huge already for matrices 10 by 10. And heuristic attack has just 0% success rate. Heuristic attack is not a solution for everything, as it turns out. Right. So another line of attack is to try to use the ultimate heuristic properties of tropical matrix powers, and to solve a problem that we call tropical two-sided discrete logarithm. In this case, we'll be considering tropical two-sided discrete logarithm with shift. So it just so happened that investigating the heuristic properties of tropical matrix powers was a problem which I've been studying maybe since 2009, and I had my approach to it, and that approach turned out to be useful when first with Annie we attacked a protocol using solution of discrete logarithm problem, tropical discrete logarithm. All right, so here is where the notions of maximum cycle mean and Kleene star are useful, because using these objects I'll now define CZ, RZ, and SZ matrices. So how are C, R, and S defined? If Z is a critical cycle of length LZ and lambda is maximum cycle mean, then we first compute matrix UZ, which is A minus lambda raised to power LZ, raised to tropical power LZ, and then we take and then CZ to be equal to this. So we have columns of UZ whenever the column index belongs to cycle Z and minus infinities otherwise. In RZ, we have rows of the matrix UZ whenever the row index belongs to the cycle Z and minus infinity otherwise. And finally, SZ is defined as a matrix where you have Aij minus lambda when Ij is in the cycle and minus infinities everywhere else. So, okay, now has my picture in front of the slide. I'll have to maybe I pressed something wrong, or I'll just proceed. Right, good that I didn't cross it out, that would have ended the meeting. Yeah. All right, so then using this C, S, and R, but I can't use this. And okay. List goes from one side. All right, so what's the ultimate periodicity? The main result about ultimate periodicity is here. It states that for an irreducible matrix, after some time, for T big enough, the matrix powers, the sequence of matrix powers will start to repeat itself. It repeats itself with certain shape. So that A raised to the power T plus gamma in terms of ordinary operations is equal to lambda multiplied by gamma plus the Tth tropical power of A. Yeah, how we can use C, S, and R in the interviews previously. It turns out that lambda T, S, Z, T, R, Z yields rows with indices in Z. And we have the same kind of explicit formula for columns with indices in Z. And this is what an attacker can use. Because an attacker can pre-compute the rows and columns with indices in Z using these formulas, and try to catch which of the powers actually give the correct critical rows and columns. Right? So, yeah. So it's one observation. However, in this periodicity result, the exponent capital T of A can be very big. This is the problem with it. And also, it requires a matrix to be irreducible, meaning that the associated D graph is strongly connected. And this property, of course, doesn't hold for arbitrary matrices. However, for critical rows and columns, for columns, rows and columns with critical index, periodicity holds already for a small enough transient of quadratic size, like n-1 multiplied by the length of the cycle. And then for all t after that, both the rows and columns with indices in that cycle z will become periodic. Yeah. So you see periodicity in the critical part of the matrix powers very quickly. Periodicity in the whole matrix, you might have to wait for a very long time, but periodicity in the critical part of tropical matrix powers will be seen quite quickly, and this is again what can be used. Right? So now what's the two-sided discrete logarithm? We are solving properly two-sided discrete logarithm of shift. The problem is as follows. Suppose that the message capital U is equal to T1 multiplied by M multiplied by D2 T2 shifted by certain scalar alpha. Yeah, this is like a message sent from Alice to Bob, only that it includes shift. Why it includes shift, we'll see later. But yeah, suppose we have such a problem. And then the problem is not actually to find exactly alpha T1 and T2 that generated this U, but to find possibly different constants tau, T1 prime and T2 prime, which give us the same message. Yeah. So attacker doesn't care about the actual parameters used by Alice or Bob. Attacker tries to generate his own parameters, which will do the job, which will allow him to reconstruct the key. Yeah. And so then one approach to the problem is to do exhaustive search. And you might ask, why does exhaustive search work? Because the parameters used by Alice T1 and T2 can be really huge. And so then this T max used by the attacker should also be large enough to include T1 and T2. This is not the case, however. This is not the case, at least when matrices D1 and D2 and M are irreducible. When all matrices are irreducible, then we have the ultimate periodicity result. This ultimate periodicity result means that there are infinite numbers of such pairs, T1 prime and T2 prime, which will be good enough for the attacker. And in particular, attacker can try to find such pair restricting Tmax to something like of the order n cubed or n to the 5. Yeah, and then it will be good. In the CSR approach, using CSR approaches, that it works also for reducible case when matrices are not required, when matrices are not guaranteed to have ultimate periodic powers. So we can use our explicit formulas for rows and columns using C, S, and R matrices. And then we know that for small enough, for big enough T1, T2, but not too big, we already have this property that a submatrix of capital U will have this expression using C, S, and R. And then the attacker can formulate a problem for himself to find T1 prime, T2 prime, and tau, which satisfy this. Yeah. Not that this is heuristic approach. So if attacker finds this T1 prime, T2 prime, and tau like that, then he will be guaranteed to reconstruct only certain part of a matrix capital U, and then hope for the best. Yeah, but this won't be guaranteed to work. But with this approach, it's actually quicker. So then what we have to do is to scan parameter for upper bar and T to upper bar between 0 and LZ minus 1 and 0 and LW minus 1 respectively. Among all these couples of parameters, we find a couples for which this difference will be the same for all ij in the submatrix. And then if we take such a couple, we will try to solve a simple mixed integer linear programming problem, which is given by the first two lines. Yeah, and so then we hope that this will have a good success. All right, so now how these ideas are used in cracking a known protocol which was published recently by Ahmed Pal and Mohan. The protocol is based on tropical algebra of pairs. So the authors tried to go away from tropical algebra to consider an extension of it. So it's a different semiring now. It's defined for pairs of numbers. And so then addition is defined entry-wise, and multiplication is defined like this. Yeah. There is some explanation why multiplication can be defined like that, but for now just accept that it's like that, and that authors of the article actually try to further complicate, create a further complication for the attacker by multiplying what we have in the multiplication by parameter C, so that we have a further upgrade of the tropical algebra of pairs, where multiplication uses these parameters. Addition is the same. Multiplication is modified by multiplying both components of the pair by C. Does this actually confuse the attacker? On one hand, yes. If you look at this, everything looks quite confused. There are so many parameters, right? C, D, right? So Alice chooses a semiring using parameter C. Bob chooses a semiring using parameter D. And then Alice also picks additional parameter K, additional parameter P, sorry. And Bob picks additional parameter Q. Then they end up with the same key. Essentially, this is a Stickel protocol based on powers over tropical algebra of pairs. So that's what it is, but with some extra complication using these parameters. Does it create extra complication for attacker? Actually not, because attacker can solve now two-sided discrete logarithm with shift. This is the problem that I explained earlier. And two-sided discrete logarithm with shift is easier than just a two-sided logarithm. But what we also need to do is we need to transform this unfamiliar algebra to familiar algebra. So matrix with entries in semiring of pairs can be transformed into matrix with entries in max plus. The resulting matrix will have dimension twice bigger. So how we do it? If we have an entry here, A111, A112, then we represent it as a 2 by 2 matrix like this. So every entry, which is a pair, is represented as a 2 by 2 submatrix. And then this 18 that lives in matrix algebra of tropical matrices dimension 2 and 3. Turns out that this is injective homomorphism. Injective homomorphism meaning that these properties hold. These properties hold. So injective homomorphisms that means that we can really represent tropical matrix algebra over the semiring of pairs using the usual tropical matrix algebra. Yeah. And the attacker then can follow it, and she can transform the message which Alice sends to both to usual tropical matrix algebra, and then solve two-sided logarithm with shift using the usual tropical matrix algebra. And then we have two approaches to tropical two-sided logarithm with shift. One is just exhaustive search, and the other is using those CSR things. Both can be applied, and they give rise to attacks on the protocol, one using exhaustive search, and then this is the success. You need to, however, keep in mind that we used only matrices with finite entries in our experience. We didn't even use any matrices with -infinity entries. That could have changed this picture. But yeah, this picture shows that the exhaustive search is successful, at least when matrices have finite entries. So then approach using CSR, this is a heuristic approach. Therefore, it's less successful. It's not guaranteed to work. And so it doesn't work when K and L, it does work very well when K and L are small, the parameters used by Alice and Bob. When these parameters are big enough, however, K and L are like this, then the success rate becomes quite big, again over 90%. All right. So yeah, now it's the end of closer to the end of the talk. We will discuss some other semirings. We're trying to extend the Stickel protocol and attack on Stickel protocol to other semirings. One of them is symmetrised semiring. Symmetrised semiring is based on algebra of pairs. How do we define it? First, we need to define the following equivalence relation, and then factor tropical semiring of pairs over this equivalence relation. Then this gives rise to, so what are the equivalence classes? Equivalence classes are of one of these three types. One class is when the pair has the second component strictly less than the first. The second class is when the pair has the first component strictly less than the second. And the third class is when both things are equal. So the first class corresponds to tropical positive elements of the symmetrized semiring. The second class corresponds to tropical negative semirings, and tropical negative elements, sorry. And then the third class is balanced elements. So this is a way how to introduce signs in tropical science. You can introduce minus. Don't have subtraction in tropical semiring, but you can introduce minus or minus subtraction, so that your tropical elements will now have sign. Right, and this is only work in the progress in the very beginning. Of course, you can implement Stickel protocol, and you can even extend limited point matrices, which we did with Dani, but now turns out that they can be extended to the case of symmetrized semiring. With attack, it's quite the situation is that you can, of course, always go to the, you can take absolute values of your tropical signed elements, and then this will give you just a tropical semiring, and you can always run a heuristic attack on the protocol over symmetrised semiring. The heuristic attack will use absolute values and will generate polynomials or exponents used by Ellison. Exponents that attacker can hope to use to regenerate the key. The success rate, however, is not very big. And then one of the problems is that the theory of linear systems like X equals to B is not developed over symmetrised semiring. That's something to do. And the success rate of an attack which uses absolute values and then CSR. So this is a heuristic for two-sided logarithm, and you see that the success rate goes down as the dimension goes up. This has been one of the results of the work of my master's student, my most recent master's. Okay, other semirings that we can consider are max min and max t. What's the max min semiring? We consider the set of real numbers joined with minus infinity plus infinity. Addition is a maximum of two numbers, and multiplication is minimum of two numbers. This forms a semiring. Max t semiring is when we have a unit interval equipped with addition, again taking max, and the role of multiplication is played by t norm. T norm, triangular norm. First, it was introduced in the context of probability by Schweitzer and Shpilrain, but then turned out that this is, of course, a purely algebraic topic. And you can see that together with max, this forms a semiring because the monotonicity axiom, T norm should be monotone with respect to both arguments. So the monotonicity guarantees that such multiplication will distribute with respect to tropical addition, so that you get a semiring. All right, and so this is part of fuzzy theory of fuzzy sets. So then this is an equation that we need to solve in Kotov-Ushakov attack. So what is this equation? U equal to O plus Z alpha beta by R alpha beta. This is known as systems of fuzzy relational equations in fuzzy sets theory. And it's been a quite popular topic, describing all solutions to fuzzy relational equations. So this has been quite popular in fuzzy sets theory, and here's the result, that if when T norm is continuous, then there is just one greatest solution to Ax equals to B. There is a finite number of minimal solutions to Ax equals to B, and the whole solution set can be described as such a union of boxes between a minimal and the greatest solution. Yes, so so then this can be used by the attacker. This can be used to actually define the Kotov-Ushakov attack over such semirings. And minimal solutions, there are algorithms to find them. And we use in particular algorithm described in the book by Dave and Kosov, because this book is publicly available on the internet. And also in the work by Zakhariev. Zakhariev has some nice works on algorithms for solving max-min and other fuzzy relational equations. So then this is the attack, just like I said. We need the greatest solution, we need all the minimal solutions, and then among the minimal solution, so you need to find a minimal solution for which this system will be solved. X alpha multiplied by y beta. In the max-min case, it's taking minimum. So then it's important to realize that when you write this in terms of usual operations, then minimum of X alpha y beta less than or equal to C alpha beta is no longer linear constant. So yeah, you can formulate it as mixed integer linear program using big M methods. But then mixed integer linear programming problems are harder than just linear programming. For this kind of reasons, We also want to consider heuristic attack, where we just want to check one box instead of checking all the boxes. And then what are the results? If we implement Stickel and polynomials and then run the Kotov-Ushakov attack as described, it's even worse than Kotov-Ushakov attack in max plus. So Alice and Bob can feel even more secure. As the dimension comes to 9, the number of minimal solutions skyrockets, and so does the time that is needed to crack the protocol. The same situation is with circulants and heuristic. Well, there is some modest success of heuristic if we consider polynomial version of Stickel protocol based on polynomials, but when we consider protocol based on circulants, success rate is 0. So yeah, that's all that I wanted to present, and there are further directions. There are a lot of things to consider when you think about Stickel protocol. You can do two things. You can study the related problems of tropical matrix algebra deeper, problems like the two-sided logarithm, which you have seen. So deeper study would be highly welcome. But you understand that in practice, if you can reduce things to max plus, it means that actually the protocols are not secure anymore. And you need to extend your horizon. You need to study other semirings and try to maybe the more elaborate semiring you study, the more elaborate implementation of Stickel protocol, the better, let's say. And this is the topic for future research. Okay, so thank you. That's more or less all I wanted to tell.
Thank you for the presentation. It was a nice presentation. Please give applause. Okay, there is a joke on the cryptography community. So whenever someone gives new proposal for protocol, and then okay, I will attack it. So it's like trying to challenge someone to attack my protocol. So that's what Professor said, the protocol based on the tropic.
As you see, you can consider different implementations of the same protocol, and then just it takes time for people to get used to it and to attack it. And then the attack might have this or that polynomial complexity, this or that complexity, and this or that success rate if it is a heuristic attack. So I can't say with certainty that everything is quite weak. You've seen that Kotov-Ushakov attack, for example, it's not really a good enough solution because it takes a lot of time. It doesn't scale, right? So then you need to consider heuristic version of this attack, but then will this heuristic version work? Or will another heuristic that you can suggest for this or that protocol actually work? But yeah, at present the situation is that no matter which protocol over max plus you have, an efficient enough heuristic attack for it is known. So in this sense, yeah. And therefore, as I said, it's interesting to extend your horizon to look at different semirings and then see whether these semirings can be reduced to max plus, whether it can be attacked by the same techniques as max plus. So in my works, I'm trying not just to suggest a new protocol, but to immediately test an existing technique for attacking it. So we, with Suleiman, we extended Stickel protocol to max min and max t semirings. Then we immediately looked at Kotov-Ushakov attack. How does it perform? What's an obvious heuristic? How does this heuristic perform, right? But what we found is that, okay, we probably don't have good idea here, but maybe someone else would have good idea. counter attack.
Any questions?
Thank you. Why choose the size of the matrix? You discuss a square matrix.
Yes.
My opinion is it will be nice if not should be a square matrix. As long as the multiplication is suitable size of. Is this possible for non-square matrix?
No. Okay. Let's see. If we consider Stickel protocol, right? Let's look at that. So we have matrix multiplication. Matrix capital M could be rectangular in principle. Then it would mean that, so
You can choose any size of matrix as long as the size is suitable.
well, we are using commutativity. In Stickel protocol in particular, we use commutativity, right? So then you need to have that A1 multiplied by A2 is equal to A2 multiplied by A1. But then if your matrices A1 and A2 are rectangular, then well, yeah, in principle, it would look possible, but no, I think it will be difficult to make that work, right? Because
For cryptography, I think it will be more exciting for difficulty to attack some.
Well, yeah, I think it's you have because you're like I said in the commutativity property, A1 multiplied by A2 should be equal to A2 multiplied by A1. Yeah. If you can make a protocol using rectangular matrices and that this property is satisfied, then you can do it.
Once more.
Yeah.
You also discussed only for the entry of the matrix is finite in the ring of minus cosine there is cosine. Since the finite this meaning the matrix is strongly connected.
Yeah, that's right. This is what I said, that this is probably an issue with our numerical experiments, and in the future we should allow for minus infinity, of course. And then see in particular how does this CSR heuristic work, and whether it is true that the exhaustive approach will fail. So indeed, we need to see.
Thank you.
Thank you for the question and answer. Another questions? Okay, Mr. Digi.
Thank you for the interesting talk. So, as you mentioned, you presented the Stickel protocol with certain semiring, and we discussed how to attack the Stickel protocol. So, I was wondering how you usually present the performance of the attack. Because in one of the topic you mentioned that this is like NP-hard or something like that, this kind of complexity. But on the other part of the topic, the other protocol, you present like the empirical or the simulation or the empirical, how does it perform, how long does it takes to attack. So what is usually the way to present the performance of the attack?
Yeah. Okay. As I said, there are difficult problems related to the Kotov-Ushakov attack. at least the current implementation of Kotov-Ushakov attack requires you to generate all the minimal covers. So then it's reasonable to expect that it won't scale. But still, we wanted to check if it scales or if it doesn't. Okay, it doesn't scale. But Kotov-Ushakov attack is guaranteed to get. That's what's good about it. That mathematically proven, that is works. But then, okay, saying, okay, generating all minimal covers, it's too hard, it takes too much time. Maybe I can do with generating one or two good enough minimal covers. And then, as you have seen, heuristic attack turns out that it has 100% circlets, the protocol based on circlets. And then it probably means that there is a mathematically provable claim about it, which we just need to formulate and prove, I think. And for the polynomials, the attack has 90%, a good success rate, which also should have some explanation. So the thing that we are close to NP card problem it doesn't necessarily mean that we can't escape from it. So there could be an escape. There could be an attack of different form, or a bit of modification of Kotov-Ushakov attack, which would avoid enumerating all the minimal covers. And you can use the particular properties of your platform, right, that you are using for implementing the protocol. Like if it's circulant matrices, then it's one situation. If it's linear point matrices, which we considered with Ani, then it's another situation. And in her dissertation, a number of heuristic attacks described, which are not related to Ushakov attack, but are just specifically designed for linear point matrices. Yeah, so the fact that there is a big hard problem related to this is, of course, interesting, but it doesn't mean that we can just stop working and say that, oh, we can't find an attack which scales very well, so this protocol is actually secure, or that it will be secure in the post-quantum world. So we can't say that. We need to find new attacks, try to find new implementations of the protocols. I think it's interesting.
Thank you. So the NP hard is the worst case, and in practice it can be better than that.
Yeah, exactly. And this is what often occurs in optimization. Okay, problem is NP hard, but you can still do a lot. Like there is no problem, right? Does the NP hardness of this problem deter people from solving? Of course not. Yeah. More and more traveling salesman problems of more and more bigger and bigger size are solved these days.
Thank you. Thank you very much.
Another question from students? Maybe I can have several questions. So my first question is, how about if the semiring that we use is not associative? Because as I understand the basics, so most of the protocols that you describe depend on the associative element. But what happens when I have new semiring which is not associative, or I have new algebraic structure?
No, that's a problem. I mean, if you there was an attempt by Mariana Durcheva and her co-author to use both maximum and minimum operations in the protocol. And the thing is that exactly because of the level of associativity, sometimes it works and sometimes it doesn't. So then the protocol, if you lack associativity, as you said, then it's you don't have an unambiguous definition of matrix files. So that definition of matrix files, it's difficult. So then the implementation of Stickel based on matrix files or polynomials becomes difficult. You can still try to do circles down, right? It seems so. But then the lack of associativity will still be a danger. Because first of all, your protocol should work, right? Yeah, so in this case, what Mariana Duccio described, the protocol sometimes worked and sometimes it didn't. Quite often it worked, but sometimes it didn't. And then Kotov with authors even wrote a paper about attacking the protocol. And then so the story is that okay, the protocol sometimes works, sometimes it didn't. It doesn't. If it works, then there is attack. And then if this attack is heuristic, then also sometimes it works, sometimes it doesn't. So it's this situation. You can still play with it, but then your protocol becomes heuristic.
That's the problem because the protocol itself is maybe not complete.
Yeah.
Or not well defined.
Yeah.
Okay, maybe another question. So it just I'm asking your opinion about the post-quantum cryptography. So it will be affected, like for example, the tropical and post-quantum cryptography, because if we already have really strong quantum computers, maybe cryptography is not a big problem anymore.
Well, first of all, you need a protocol which will be hard to crack ordinary computers, right?
Yes.
That's the thing. It quite often happens, I think, in cryptography that people claim that their protocol is hopeful also in the post-quantum method. But then it turns out that it is breakable without any. So you need to start with a limited level. Right.
Thanks. Any questions from students? Ilham?
From this is
yeah.
I from the
Any question from Zoom? I already asking in the chat, but no one replied.
Yeah.
Ilham?
Yeah. Okay.
You not asking something? Okay, good. Well, maybe the next one is Fikri. So Ilham is the new professor students. He's working on Max Plus.
Okay, thanks for the meeting. My name is Muanalifah. With your presentation. What's your opinion about Idempotent algebra with quantum computation? This relationship about that. Especially about operator max and min in quantum computation.
Yeah, well,
maximum. I think
Yeah.
it's possible.
To be honest, I don't have much knowledge about that. Yeah, so like I said, you first should have a protocol which will be secure in non-quantum, right? Then you can hope that there will be a version which will be secure also against quantum computations. Yeah.
Okay, thank you. Another question? Maybe the last one? Juba? Okay, I think that's all for this session. So please give applause to Professor Sergey. I think before we formally end the meeting, we can take a picture together. Mr. Alu, can you help us to take picture?
Ali.
much better. Okay. Anyone? Everyone, please come forward. Come on, let's go. Let's go. Most of you. Come on, guys. Two lines. Tutup dia yang cowok-cowok. Fun.
Okay. 1, 2, 3. 1, 2, 3. This time. Satu, dua, tiga.
Okay, thank you for coming to this lecture. So for my students, you will have homework. And also thank you for anyone who joined us in the Zoom meeting. See you on the next occasion, and wassalamualaikum warahmatullahi wabarakatuh. On Saturday. On Saturday. You want to have or maybe yeah. So the next